Good evening, and welcome to The Sleepy Scientist. I'm very glad you've chosen to spend a little of your night here. Before we travel too far from home, I'd love to know where you're listening from tonight. Perhaps you're already tucked into bed, perhaps you're stretched out on the sofa, or maybe this is keeping you company during one of those quiet hours when the rest of the house has gone still. Wherever you happen to be, get comfortable, let your shoulders relax, and allow everything outside this moment to become a little less important. And if you prefer these episodes without a glowing screen nearby, The Sleepy Scientist is also on Spotify. You'll find the link waiting for you in the description, so whenever you're ready, you can put the phone down, close your eyes, and simply listen. If these slow journeys through science have become part of your evenings, leaving a like or subscribing is a small thing that makes an enormous difference to the channel. And to everyone who has already done that, thank you. It's wonderful knowing that these strange little trips through the universe are being shared with so many of you. Tonight, we're going to travel outward, past Saturn and its rings, beyond the methane lakes of Titan and the icy geysers of Enceladus, past Uranus and Neptune, and into regions where planets give way to frozen worlds, the solar wind fades into interstellar space, and even the sun's gravity begins to compete with the pull of the wider galaxy. I'll try not to make any of that too exciting, although discovering that the solar system may extend more than a light year from the sun is perhaps not ideal material for an early night. So, make yourself comfortable, and let's begin. Where does the solar system actually end? Most of us first meet the solar system in a diagram that looks wonderfully tidy. The sun sits in the middle, the planets are arranged around it in neat little orbits, and somewhere beyond Neptune the picture simply seems to stop. It is useful for learning the names of the planets, but as a map of the solar system itself, it leaves almost everything out. The real solar system is vastly larger, far emptier, and much harder to give a clean outer boundary. If you asked where the solar system ends, one perfectly reasonable answer would be Neptune. Neptune is the eighth and most distant major planet, orbiting the Sun at an average distance of around 30 astronomical units. 1 astronomical unit is roughly the average distance between Earth and the Sun, about 150 million kilometers. By the time we reach Neptune, we are already about 4.5 billion kilometers from the Sun. But if Neptune is the end, then Pluto would somehow be outside the solar system for much of its orbit, along with countless other icy objects that unquestionably orbit the Sun. So Neptune cannot really be the whole answer. Beyond Neptune lies the Kuiper Belt, a broad region filled with frozen remnants left over from the formation of the planets. Pluto belongs to this population, along with dwarf planets and smaller bodies made largely from rock and ices. The main part of the Kuiper Belt extends for tens of astronomical units beyond Neptune. If we define the solar system by the family of substantial objects orbiting the Sun in a broad flattened region, then perhaps this is where the edge begins to make more sense. Except the Sun reaches much farther still. The Sun is constantly releasing a stream of charged particles known as the solar wind. These particles race outward in every direction and carry part of the Sun's magnetic field with them. Together they create an enormous bubble around the planets called the heliosphere. Eventually, the solar wind becomes so weak that it can no longer dominate the surrounding interstellar environment. The boundary where this happens is called the heliopause. This is a particularly interesting candidate for the edge of the solar system, because it is something spacecraft have actually crossed. Voyager 1 entered the region beyond the heliopause in 2012, and Voyager 2 crossed it in 2018. Both spacecraft had travelled more than 100 astronomical units from the Sun, before entering what scientists describe as interstellar space. That sounds fairly conclusive. If a spacecraft has entered interstellar space, surely it has left the solar system. Not quite. It has left the sun's solar wind behind. It has not left the sun's gravity behind. Gravity does not simply switch off at a particular distance. The gravitational attraction of the sun becomes weaker and weaker as you move farther away, but there is no invisible wall where it suddenly disappears. Even beyond the heliopause, extremely distant objects can remain gravitationally bound to the sun, and that takes us to a much more distant possible edge. Far beyond the Kuiper Belt, astronomers think there is an immense population of frozen bodies known as the Oort Cloud. Unlike the relatively flat arrangement of the planets in Kuiper Belt, the Oort Cloud is thought to form something closer to a vast spherical shell surrounding the solar system. We have never directly seen the Oort Cloud as a complete structure. Its existence is inferred largely from the behaviour of long-period comets, which can arrive from enormous distances and from many different directions. Estimates vary, but the outer Oort Cloud may extend tens of thousands of astronomical units from the Sun, perhaps reaching something on the order of 100,000 astronomical units in its most distant regions. At those scales, we are no longer talking about a little extension beyond Neptune. We are talking about distances measured in a significant fraction of a light year. And even there, drawing a sharp boundary becomes difficult. At such enormous distances, the Sun's gravitational hold becomes increasingly vulnerable to disturbances from passing stars and from the gravitational field of the Milky Way itself. An object may remain loosely bound to the Sun for millions or billions of years, only for a passing star to alter its orbit enough to send it inward, push it farther outward, or remove it from the solar system altogether. So the outer edge is not really a wall. It is more like a gradually fading border between one gravitational neighbourhood and another. This is why several different statements can all be correct at the same time. Neptune is the end of the major planets. The Kuiper Belt marks the distant realm of many of the solar system's known icy worlds. The heliopause marks the outer edge of the Sun's solar wind bubble and the beginning of interstellar space. And the Oort Cloud may represent the farthest meaningful reach of the population still gravitationally associated with the Sun. To understand how quickly the familiar solar system begins to change, we can start much closer in. Saturn is already almost 10 times farther from the Sun than Earth is. Sunlight is much weaker there. Journeys take years rather than months. Temperatures are low enough for substances that would behave very differently near Earth to remain frozen across moons and rings. And surrounding Saturn are worlds that immediately show us just how strange the outer solar system becomes. There are enormous rings made from countless pieces of ice. There is Titan, where methane forms clouds, falls as rain, carves channels and gathers in lakes and seas. There is Enceladus, a small frozen moon-spraying material from a hidden ocean directly into space. From there, Uranus and Neptune wait farther out, followed not by emptiness, but by an enormous territory of frozen objects. Invisible boundaries, ancient comets and distances so large that the 8 planets begin to look less like the whole solar system and more like a tightly packed little group gathered very close to its centre. The solar system does have edges. The difficulty is deciding which edge we mean. Once we move beyond the familiar planets, distance begins to behave almost like a different subject altogether. On Earth, we are comfortable with kilometres. A journey of 100 kilometres feels substantial. A journey of 1,000 kilometres can take us across countries. Even the circumference of Earth, at roughly 40,000 kilometres, is large enough to feel difficult to picture clearly. But those numbers become almost useless once we begin moving through the solar system. Astronomers therefore use a much larger unit called the astronomical unit. 1 astronomical unit is approximately the average distance between Earth and the Sun, around 150 million kilometers. That single distance is already large enough that sunlight, travelling at almost 300,000 kilometers every second, takes a little over 8 minutes to cross it. So when you look at the Sun, you are not seeing it exactly as it is now. You are seeing sunlight that began its journey several minutes earlier. At first, the astronomical unit makes the solar system easier to describe. Earth sits roughly 1 astronomical unit from the Sun. Mars averages about 1.5 astronomical units away. Jupiter is a little more than 5 astronomical units from the Sun. Then we reach Saturn. Saturn orbits at an average distance of about 9.5 astronomical units. In kilometers, that is roughly 1.4 billion kilometers from the Sun. Even light needs around 80 minutes to travel from the Sun to Saturn. That immediately changes the feeling of the journey. A signal from Earth cannot simply reach a spacecraft near Saturn instantly. Depending on the positions of Earth, Saturn, and the spacecraft, radio communication takes well over an hour in one direction. There is no possibility of steering a spacecraft there with the kind of immediate response we might expect from an aircraft or a vehicle on Earth. Commands have to be planned, transmitted, and then patiently awaited. Farther out, Uranus orbits at roughly 19 astronomical units. Sunlight reaching Uranus has travelled for more than 2.5 hours. By the time you saw something happen there through a perfect telescope, that event would already be hours old. Neptune lies farther still, at an average distance close to 30 astronomical units, or around 4.5 billion kilometers from the Sun. Light takes a little over 4 hours to travel from the Sun to Neptune. A message sent from Earth toward a spacecraft near Neptune therefore takes hours to arrive, and any reply takes hours more to return. Even at the speed of light, a simple exchange becomes an all-day conversation. And Neptune is still nowhere near the end. The main Kuiper Belt begins around the region of Neptune's orbit and extends broadly outward to around 50 or 55 astronomical units. This region contains Pluto and many other icy bodies, along with objects occupying resonant, inclined or eccentric orbits. Some members remain relatively close to this broad zone. Others travel much farther from the Sun. The scattered disk contains bodies with highly elongated orbits that can carry them far beyond the main Kuiper Belt. Detached objects can reach still greater distances. By this stage, even the astronomical unit begins to lose some of its intuitive usefulness. 50 astronomical units is already about 7.5 billion kilometers. 100 astronomical units is roughly 15 billion kilometers. The numbers remain accurate, but they stop behaving like distances we can naturally imagine. The Voyager spacecraft helped make this scale slightly more tangible. Voyager 1 and Voyager 2 both travelled far beyond the planets before reaching the heliopause, the boundary where the outward-flowing solar wind gives way to the surrounding interstellar environment. Their crossings took place at distances of roughly 120 astronomical units from the Sun, although the exact distance differed between the two spacecraft. That means the bubble produced by the Sun's charged particles extends several times farther than Neptune's orbit. If Neptune marks the end of the major planets at around 30 astronomical units, then the heliopause lies roughly 4 times farther from the Sun. And still, the solar system may continue enormously farther. The Oort Cloud is thought to begin thousands of astronomical units from the Sun, and perhaps extend outward to something on the order of 100,000 astronomical units. At that point, astronomical units themselves begin to sound awkward. 100,000 astronomical units is around 15 trillion kilometers. So another unit becomes useful. The light year is the distance light travels in 1 year, roughly 9.5 trillion kilometers. An outer Oort cloud extending toward 100,000 astronomical units would therefore reach roughly 1.5 light years from the Sun. Suddenly, we are using a unit normally associated with the distances between stars. The nearest star system beyond our own, Alpha Centauri, lies a little more than 4 light-years away. So if the most distant estimates for the Oort cloud are approximately correct, the Sun's gravitational family may extend a surprisingly large fraction of the way toward neighbouring stars. This is one reason ordinary diagrams of the solar system can be so misleading. The planets are usually drawn much too large and far too close together. If they were shown at their correct sizes and distances on the same page, most of them would be little more than invisible specks separated by enormous stretches of blank space. And if we attempted to include the Oort cloud on the same scale, the planetary region would collapse into a tiny feature near the centre. A useful way to imagine this is to compress the solar system. Suppose the distance from the Sun to Earth were reduced to just 1 metre. Saturn would then orbit roughly 9.5 metres away. Uranus would be about 19 metres away. Neptune would sit around 30 metres from the Sun. The main Kuiper Belt would stretch outward to roughly 50 metres. The heliopause would lie around 120 metres away. But an outer Oort cloud reaching 100,000 astronomical units would extend for around 100 kilometres on that same scale. Earth, Saturn, Uranus, Neptune, Pluto, and the entire familiar planetary system would all be clustered within the first few dozen metres. The outer gravitational structure of the solar system would continue across the distance of a substantial road journey. This gradual change in the units we use tells us something important. Close to the Sun, we talk comfortably in millions of kilometres. Across the planets, astronomical units become more useful. Farther out, tens of thousands of astronomical units begin to blur into fractions of a light year. And with every change in scale, the meaning of the solar system's edge changes with it. The planets occupy only a small central part. The Kuiper Belt extends farther. The heliosphere reaches farther still in another sense. And the Sun's gravitational influence may continue so far outward that the language of planetary distance finally gives way to the language of the stars. By the time we reach Saturn, the solar system has begun to feel noticeably different. Saturn is the 6th planet from the Sun, and the 2nd largest planet in the solar system, smaller only than Jupiter. It orbits at an average distance of roughly 9.5 astronomical units, meaning it is almost 10 times farther from the Sun than Earth is. At that distance, sunlight is far weaker. Temperatures are much lower. Substances that behave as gases or liquids in warmer parts of the solar system can remain frozen across moons, rings, and smaller bodies. Water becomes hard ice. Ammonia can freeze. Methane can survive in environments that would be impossible much closer to the Sun. This colder chemistry becomes one of the defining features of the outer solar system. Saturn itself, however, is not a giant frozen world. It is a gas giant composed predominantly of hydrogen and helium, the same 2 elements that dominate the Sun. There is no solid surface where a spacecraft could simply land. As we move downward through Saturn's atmosphere, the gas becomes progressively denser under increasing pressure. Hydrogen is compressed into deeper fluid layers, eventually reaching conditions where it can behave as metallic hydrogen, an unusual state in which electrons move more freely through the material. Farther toward the centre lies a dense region containing heavier elements, probably including rock, ice, and other materials mixed under extraordinary pressure. The exact structure of Saturn's interior is still being studied. It is far more complicated than a neat rocky core surrounded by simple layers of gas. Saturn is enormous. Its diameter is roughly 120,000 kilometers, making it more than 9 times wider than Earth. Yet despite its size, Saturn is the least dense planet in the solar system. Its average density is lower than that of liquid water. This occasionally leads to the cheerful observation that Saturn would float if someone could find an ocean large enough to put it in. Finding the ocean would probably be the more difficult part. Saturn also spins remarkably quickly. One rotation takes only about 10 3/4 hours. A planet more than 9 times wider than Earth completes a day in less than half the time Earth does. That rapid rotation causes Saturn to bulge noticeably around its equator and flatten near its poles. Its year is a very different matter. Saturn takes almost 30 Earth years to complete a single orbit around the Sun. A person somehow born on Saturn at the beginning of one Saturnian year would be approaching 30 years old before celebrating their first birthday according to the planet's orbit. But Saturn is more than one planet travelling around the Sun. It sits at the centre of an enormous miniature system of its own. There are rings extending hundreds of thousands of kilometres across. There are numerous moons ranging from tiny, irregular fragments to Titan, a moon larger than the planet Mercury. There is Saturn's magnetic field and the vast magnetosphere shaped by it. There are streams of charged particles. There are gravitational resonances connecting moons and rings across enormous distances. Seen this way, Saturn begins to resemble a small planetary system within the larger solar system. Human beings knew of Saturn long before telescopes existed. It is bright enough to be seen with the unaided eye and was observed by ancient civilizations thousands of years ago. But for almost all of human history, Saturn was simply a wandering point of light. Even after the invention of the telescope, it took generations to understand what surrounded it. The transformation in our knowledge accelerated dramatically once spacecraft began travelling there. Voyager 1 passed Saturn in 1980. Voyager 2 followed in 1981. Their cameras and instruments revealed details of the rings, atmosphere, magnetic environment, and moons that could never have been seen properly from Earth. Then came a much more ambitious visitor. The Cassini-Huygens mission was a collaboration involving the National Aeronautics and Space Administration, the European Space Agency, and the Italian Space Agency. Cassini arrived at Saturn in 2004 and entered orbit, beginning one of the most productive planetary exploration missions ever attempted. For 13 years, the spacecraft repeatedly travelled through the Saturnian system. It watched storms move across Saturn's atmosphere. It studied the structure of the rings. It flew past moons again and again. It measured gravity, magnetic fields, particles, ice, dust, and gases. The Huygens probe separated from Cassini and descended through the atmosphere of Titan, eventually landing on its surface in 2005. Cassini also transformed our understanding of the small moon Enceladus after observing enormous plumes of water-rich material erupting from fractures near its south pole. These discoveries turned Saturn from a beautiful distant planet into a place filled with active environments. Its moons revealed internal oceans, its rings revealed the delicate effects of orbital resonance and tidal gravity. Its atmosphere revealed storms and circulation operating under conditions very different from those on Earth. Titan showed that complex chemistry, weather, rivers, lakes and seas can exist using substances other than liquid water at the surface. Enceladus showed that a small frozen moon can contain a liquid ocean hidden beneath its crust and release material from that ocean directly into space. Saturn therefore marks an important change in the journey outward. The outer solar system is colder, darker, and more distant, but it is not necessarily quieter. In some ways it becomes more varied. Cold temperatures preserve volatile substances that disappear from warmer worlds. Powerful tidal forces can maintain geological activity inside moons far from the Sun. Gravity organizes countless bodies into rings, resonances, and orbital families. Cassini's mission ended in 2017. By then, engineers faced a problem created by the spacecraft's own success. Cassini had discovered that moons such as Enceladus possessed environments of considerable astrobiological interest. If the spacecraft were eventually left uncontrolled, there was a small possibility that it could collide with one of these moons and contaminate it with material carried from Earth. So Cassini was deliberately directed into Saturn's atmosphere. During its final orbits, it repeatedly passed through the narrow region between Saturn and its innermost rings, collecting measurements that had never previously been possible. Then it entered the atmosphere and was destroyed. It was an unusually thoughtful end for a spacecraft. After travelling billions of kilometres and spending more than a decade revealing Saturn's secrets, Cassini disappeared into the planet it had spent so long studying, and many of the questions it left behind begin with the feature that makes Saturn instantly recognisable. From Earth, the rings can appear almost smooth. They look like a single elegant structure wrapped around the planet. Up close, nothing could be further from the truth. The rings are not solid. They are made from an astonishing population of separate particles, each moving around Saturn under the same fundamental laws of gravity that govern planets around the Sun. From tiny grains to large blocks of ice, billions upon billions of individual objects combine to create something that, from a distance, looks almost impossibly perfect. When Galileo Galilei first turned a telescope towards Saturn in 1610, he saw something that made almost no sense. His instrument was far too crude to reveal the rings clearly. Instead, Saturn appeared to have strange companions attached to either side, almost as though the planet had grown a pair of ears. Galileo returned to Saturn repeatedly, but the view only became more confusing. As Saturn moved through its orbit, the angle of the rings changed from Earth's perspective. At times they appeared broad and obvious. At other times they seemed to vanish almost completely. It was not until several decades later that Christian Huygens offered the correct interpretation. Saturn was surrounded by a thin, flat ring that did not touch the planet. Then Giovanni Domenico Cassini observed that the ring system itself was divided. The most prominent dark gap between the bright A ring and B ring became known as the Cassini division. What looked simple from Earth was already beginning to reveal structure. Modern observations have taken that idea much further. Saturn's rings are not solid disks. They are enormous populations of individual particles, each travelling around Saturn in its own orbit. Most of the material is water ice, mixed with smaller amounts of rocky and dusty material. Some particles are tiny grains, others are chunks the size of houses. There are probably countless objects spanning a wide range of sizes, all sharing the same broad region of space. From a distance, this collection blends together into smooth bands of light. Up close, it is more like an immense orbital traffic system. Every particle is being guided primarily by Saturn's gravity, and importantly, not every part of the rings moves at the same speed. Material closer to Saturn travels around the planet faster than material farther away. This is exactly what we expect from orbital mechanics. A particle in a lower orbit must move more quickly to remain in that orbit, so the rings do not rotate as one rigid object. If you painted a line across the entire ring system, that line would quickly become stretched and distorted because its inner parts would move ahead of its outer parts. That alone tells us that the rings are fundamentally dynamic. They are also extraordinarily thin compared with their width. The main rings stretch across hundreds of thousands of kilometers from one side of Saturn to the other, yet many parts may be only tens of meters thick. That makes them proportionally far thinner than a sheet of paper. The main system is divided into several named regions. Beginning close to Saturn is the faint D ring, followed by the brighter C ring and then the massive B ring. Farther out lies the Cassini division, followed by the A ring. Beyond that sits the narrow and complicated F ring, while more distant structures include the G ring and the broad E ring. These divisions are not arbitrary. Many of them are shaped by gravity. Saturn's moons constantly disturb the ring particles, and some of the most beautiful patterns in the system are created by these repeated gravitational interactions. Mimas, for example, produces orbital resonances that help shape gaps within the rings. A resonance occurs when the orbital periods of two objects form a simple repeating relationship. Small gravitational tugs then occur again and again in similar positions, allowing tiny effects to build over time. Other moons interact with the rings much more directly. Pan travels within the Encke gap in the A ring. Daphnis orbits inside the Keeler gap and can pull nearby ring particles vertically, creating rippling structures along the edges of the gap. Prometheus and Pandora interact with the narrow F ring, producing knots, strands, clumps, and shifting features. The ring system is therefore not a static arrangement frozen in place. It is constantly being sculpted. Another important idea is the Roche limit. This is a region around a planet where tidal forces can become strong enough to prevent loosely held material from gathering into a large moon, or in some circumstances can tear apart a body that lacks enough internal strength to resist the difference in gravitational pull across it. Saturn's rings lie largely within this kind of environment. The side of an object facing Saturn feels a slightly stronger gravitational pull than the side facing away. Across a sufficiently large or weak object, that difference can become important. This helps explain why so much material near Saturn remains spread into rings rather than simply assembling into one large moon. But the exact origin of the rings remains uncertain. One possibility is that they formed from the remains of an icy moon that was shattered by a collision or torn apart by tidal forces. Another is that several smaller icy bodies contributed material over time. There is also continuing debate about the age of the bright main rings. Their unusually clean, icy appearance has sometimes been interpreted as evidence that they may be relatively young compared with Saturn itself, because a very ancient ring system should gradually accumulate darker dust and debris. However, ring material can be recycled, redistributed, buried, exposed, and altered by collisions and interactions with Saturn's atmosphere and moons. That makes the problem much less straightforward than simply measuring how dirty the ice appears. There may not be one moment when the entire ring system suddenly formed. Different parts could have different histories. Some material may have been lost and replaced. Some may have been broken apart and reassembled repeatedly. And one of Saturn's rings is being supplied with fresh material even now. The broad E ring is very different from the dense, bright main rings. Its particles are extremely small and widely spread. Much of that material comes from Enceladus. This little icy moon sprays water-rich particles from fractures near its south pole. Some of those particles escape Enceladus and enter orbit around Saturn, gradually spreading out to help form the E ring. So one of Saturn's moons is literally feeding part of the ring system. That connection captures what makes Saturn so scientifically rich. The planet affects the moons reshape the rings exchange material with the moons. Tidal forces heat interiors. Orbital resonances rearrange particles. Ice, dust, gravity and motion are tied together across enormous distances. From Earth, Saturn's rings look almost impossibly calm and ordered. In reality, they are the visible result of countless objects continually responding to gravity. And hidden within that elegant structure is a clue that the outer solar system is not simply a collection of isolated worlds. It is a network of systems within systems, each one influencing the others. Titan is one of those worlds that becomes stranger the longer you look at it. It is Saturn's largest moon and the second largest moon in the solar system. With a diameter of more than 5,000 kilometers, Titan is actually wider than the planet Mercury. Christian Huygens discovered it in 1655, although he could have had little idea just how unusual the distant point of light would eventually prove to be. Titan is the only moon in the solar system known to possess a dense, substantial atmosphere. At its surface, the atmospheric pressure is roughly 1.5 times that experienced at sea level on Earth. The atmosphere is composed predominantly of molecular nitrogen, making Titan surprisingly similar to Earth in one respect. But mixed into that nitrogen is methane. High in the atmosphere, sunlight and energetic particles break apart molecules and drive complicated chemical reactions. The products combine into larger organic molecules, helping create the thick orange haze that hides Titan's surface from ordinary visible light observations. For many years this haze made Titan extraordinarily frustrating. Astronomers knew there was a large world underneath it, but they could barely see what that world looked like. The Cassini spacecraft changed that. Because visible light could not easily penetrate the haze, Cassini relied heavily on radar and infrared instruments to study the landscape below. Slowly an entire world emerged. There were enormous dune fields stretching across equatorial regions. There were channels that appeared to have been carved by flowing liquid. There were plains, mountains, possible cryovolcanic features, and vast dark regions near the poles that turned out to be lakes and seas. Titan has something remarkably close to a hydrological cycle, except there is very little liquid water flowing across its surface. Instead, the working fluids are mainly methane and ethane. Methane can evaporate from lakes and seas. It can enter the atmosphere, form clouds, condense, fall as rain, run through channels, collect in depressions, and eventually return to larger bodies of liquid. The basic pattern sounds strangely familiar. Evaporation, clouds, rainfall, rivers, lakes, seas, but the chemistry is entirely different. Titan's surface temperature is around 179 degrees below 0 Celsius. At temperatures like these, water ice is so hard that it behaves more like rock does on Earth. Water forms much of the landscape itself. Methane takes on the role normally played by water. Near Titan's North Pole are some of the largest known bodies of stable surface liquid anywhere beyond Earth. Kraken Mare is the largest. Ligeia Mare is another enormous sea, filled predominantly with liquid methane along with other hydrocarbons. Smaller lakes and connecting channels surround them. The existence of these seas means Titan possesses coastlines, islands, shorelines, drainage systems, and landscapes modified by weather. If you could somehow stand safely on the surface, the scenery might feel oddly recognizable at first glance. There could be clouds overhead, there could be rain, there could be a shoreline in the distance. Then you would remember that the rain is methane, the sea is filled with hydrocarbons, the rocks beneath your feet may be water ice, and Saturn is hanging somewhere beyond the orange haze. The Huygens probe gave humanity its first direct experience of this landscape. After separating from Cassini, Huygens entered Titan's atmosphere and descended by parachute in January 2005. For more than 2 hours it measured the atmosphere while slowly falling toward the surface. Its cameras revealed branching channels and terrain that looked as though flowing liquid had shaped it. Huygens eventually landed on a relatively flat region, scattered with rounded objects composed largely of water ice. Their smooth shapes were consistent with material that had been transported or modified by liquid, much as stones in an earthly river can become rounded over time. Titan is not simply a frozen copy of Earth. However, its methane climate raises an important problem. Sunlight gradually destroys methane in the upper atmosphere. Over geological time, the methane should disappear unless some process replaces it. Scientists have therefore investigated possible reservoirs inside Titan and mechanisms capable of releasing methane into the atmosphere. Seasonal changes also affect clouds, rainfall, winds, and the distribution of methane around the Moon. One Titan year is the same as one Saturn year, almost 30 Earth years, so its seasons unfold very slowly by human standards. Beneath all of this may lie another environment entirely. Evidence from Titan's gravity, rotation, and interior modelling suggests that a deep ocean of liquid water probably exists beneath its frozen outer shell. So Titan may contain two profoundly different liquid environments. At the surface are hydrocarbon lakes and seas dominated by methane and ethane. Far below lies a probable water-rich ocean concealed beneath kilometres of ice. This makes Titan particularly interesting when scientists think about habitability and the chemistry that can precede life. Complex organic molecules are abundant there. Carbon chemistry is active. There are liquids, energy sources, and environments unlike anything found naturally on Earth's surface. But these ideas have to be handled carefully. Complex chemistry is not the same thing as life. Prebiotic chemistry, meaning chemistry capable of contributing to the processes that may precede biology, is not evidence that biology has actually developed. And there is currently no confirmed evidence of life on Titan. That distinction is important precisely because Titan is so tempting. It offers natural laboratories for studying how organic chemistry behaves under conditions radically different from those on Earth. The National Aeronautics and Space Administration plans to investigate those environments with Dragonfly, an unusual robotic mission designed to travel between multiple locations on Titan. Dragonfly is a rotorcraft rather than a conventional rover. Titan's dense atmosphere and relatively weak gravity make powered flight unusually practical, allowing the spacecraft to move across much greater distances than a wheeled vehicle could easily cover. Its instruments are intended to examine surface composition, organic chemistry, geological processes, and the conditions that may help scientists understand how far complex chemistry can progress before biology is involved. Titan therefore changes an assumption that is easy to carry into the outer solar system. Travelling farther from the Sun does not mean travelling into chemical inactivity. Sunlight becomes weaker, temperatures fall dramatically, water freezes hard enough to become landscape, yet chemistry continues. Weather continues. Landscapes continue to evolve. On Titan, a cold world more than 1 billion kilometres from the Sun has clouds moving through a nitrogen sky, methane falling as rain, rivers carving channels, and dark seas waiting beneath an orange haze. The outer solar system is not simply where activity fades away, it is where familiar processes begin using unfamiliar ingredients. Enceladus does not look like the sort of world that should be particularly interesting. It is small, only about 500 kilometers across, and its surface is covered almost entirely in bright water ice. From a distance it appears pale, frozen, and quiet. For a long time, that was more or less what scientists expected it to be. Then the Cassini spacecraft began looking closely. What Cassini found transformed Enceladus from a minor icy moon into one of the most scientifically important places in the outer solar system. Near the moon's south pole are long, roughly parallel fractures in the ice. These features became known as tiger stripes because of the way they appear across the surface. Cassini discovered that these fractures were warmer than the surrounding terrain. More surprisingly, enormous plumes of material were escaping from them. Water vapor, tiny ice grains, and other particles were being fired directly into space. Enceladus, it turned out, was not simply frozen. Something active was happening underneath the ice. Cassini flew through the plumes repeatedly, allowing its instruments to sample some of the material directly. The spacecraft detected water vapor, salts, carbon-bearing compounds, and particles of silica, along with other substances. This immediately raised an extraordinary possibility. The material escaping from Enceladus appeared to be coming from liquid water beneath the surface. Further measurements strengthened that interpretation. Observations of Enceladus's gravity showed that its interior did not behave like a completely solid frozen body. Small variations in the way the moon rotates also provided important evidence. Enceladus wobbles slightly as it travels around Saturn, and the size of that motion is difficult to explain if the outer ice shell is attached directly to a solid interior. Instead, the evidence points toward a global, or nearly global, liquid water ocean lying beneath the ice. So beneath a moon that looks almost perfectly frozen from the outside, there may be an entire hidden ocean. The obvious question is how that ocean can remain liquid so far from the Sun. Sunlight at Saturn is much weaker than it is at Earth. Solar heating alone cannot explain the activity seen at Enceladus. The main source of energy appears to be tidal heating. Enceladus does not travel around Saturn in a perfectly circular orbit. Its orbit is slightly eccentric, meaning its distance from Saturn changes as it moves. Because Saturn's gravitational pull becomes stronger when Enceladus is closer and weaker when it is farther away. The moon is repeatedly stretched and relaxed. The effect is subtle, but it happens constantly. That repeated flexing produces friction inside Enceladus and converts mechanical energy into heat. Orbital interactions with other moons help maintain the eccentricity of Enceladus's orbit, preventing it from simply settling into a perfectly circular path. As a result, the moon continues to be gently squeezed by Saturn again and again. That internal heating helps keep water liquid beneath the outer shell, and the evidence suggests that this water may be interacting directly with rock. Cassini detected tiny silica particles in the plume material. The best explanations for those particles involve warm water interacting with silicate rock beneath the ocean. On Earth, similar kinds of water-rock interactions occur around hydrothermal environments on the ocean floor. This does not mean Enceladus definitely has hydrothermal vents identical to those found on Earth, but the evidence is consistent with some form of warm hydrothermal activity occurring where the ocean meets the rocky interior. That matters because environments involving liquid water, rock, heat, and chemical reactions can produce useful sources of chemical energy. And this is where Enceladus becomes especially interesting when scientists think about habitability. Life as we know it requires more than simply the presence of water. A potentially habitable environment generally needs persistent liquid water. Biologically important elements such as carbon, hydrogen, nitrogen, oxygen, phosphorus and sulfur, sources of usable energy, and enough environmental stability for complex chemistry to continue over meaningful periods of time. Enceladus appears to possess several of these ingredients. There is liquid water. There are carbon-bearing compounds. There are salts and evidence of chemical interactions between water and rock. There are possible sources of chemical energy, and the ocean may have existed for a considerable length of time. But one distinction is absolutely essential. Habitability is not the same as inhabited. Finding conditions in which life might be able to exist does not mean that life actually exists there. No direct evidence of organisms has been discovered on Enceladus. No spacecraft has detected cells, metabolism, reproduction, or any unambiguous biological process. What scientists have found is an environment that appears to contain several ingredients associated with habitability. That makes Enceladus exciting precisely because the evidence is strong enough to justify deeper investigation without requiring us to leap beyond what has actually been observed. And unusually, this hidden ocean may be relatively accessible. On many icy moons, studying the subsurface ocean would require somehow drilling through kilometers of ice. Enceladus does something rather helpful. It throws some of its ocean into space. The plumes rising above the South Pole naturally carry material from beneath the surface into an environment where spacecraft can fly directly through it. In effect, the Moon provides samples without requiring us to land, drill, or melt through the crust. Some of the particles escaping Enceladus do not leave the Saturnian system. Instead, they spread around Saturn and help maintain the broad E-ring. So the same hidden ocean that makes Enceladus fascinating as a potentially habitable environment also contributes material to one of Saturn's outer rings. The connection between Moon and ring is happening continuously. More recently, the James Webb Space Telescope observed an enormous plume of water vapor extending thousands of kilometers from Enceladus. The observation showed water spreading far beyond the Moon itself and feeding material into the surrounding Saturnian environment. For such a small world, Enceladus has an extraordinary reach. Its surface may look frozen and still. Its interior is anything but. Beneath the ice is liquid water. Saturn's gravity supplies heat. Water interacts with rock. Material escapes through fractures and travels into space. And as we continue farther from the Sun, Enceladus leaves us with an important lesson. Cold does not necessarily mean dead. A world can sit more than 1 billion kilometers from the Sun, wrapped in ice and receiving only a small fraction of the sunlight reaching Earth, while still hiding an active ocean beneath its surface. The outer solar system may look quiet, but sometimes all that activity is simply happening underneath. Uranus is where the outer solar system begins to feel genuinely remote. For most of human history, nobody knew it was there. Mercury, Venus, Mars, Jupiter and Saturn are all bright enough to be seen without a telescope, and they had been watched since ancient times. Uranus was different. It remained hidden in plain sight until William Herschel observed it through a telescope in 1781. At first, Herschel thought he had discovered a comet. Continued observations showed that the object was following the kind of orbit expected from a planet. Uranus therefore became the first planet in recorded history to be recognized through telescopic observation rather than inherited from ancient astronomy. Its discovery immediately expanded the known solar system. Saturn had seemed unimaginably distant. Uranus was roughly twice as far from the Sun. Its average orbital distance is about 19 astronomical units, placing it nearly 3 billion kilometers from the Sun. Sunlight takes roughly 2 hours and 40 minutes to reach it. By the time sunlight arrives at Uranus, its intensity has fallen dramatically compared with what Earth receives. The planet inhabits a colder, dimmer environment, and its composition reflects a different balance of materials from the gas giants Jupiter and Saturn. Uranus is usually described as an ice giant. The word ice can be slightly misleading. It does not mean that Uranus is simply a giant frozen ball covered in ordinary ice. Instead, the classification refers largely to the greater importance of substances such as water, ammonia, methane, and related heavier compounds within its interior. These materials are often called ices in planetary science because they condensed as solid material under cold conditions in the early solar system. Inside Uranus today, however, extreme pressure and temperature mean they may exist as hot, dense fluids rather than familiar frozen substances. Above these deeper layers lies an atmosphere dominated by hydrogen and helium, with methane playing an important role in the planet's appearance. Methane absorbs red wavelengths of sunlight more effectively than blue and green wavelengths. As a result, some of the light reflected back into space gives Uranus its characteristic pale blue-green colour. From a distance, the planet can look remarkably calm. For a long time, this contributed to the idea that Uranus was almost featureless compared with Jupiter, with its enormous belts and storms, or Saturn, with its dramatic ring system. But the apparent stillness is deceptive. Uranus has atmospheric circulation, clouds, haze layers, changing storms, and weather systems that become more visible as observing techniques improve. Its most famous feature, however, is not its colour, it is its orientation. Uranus has an axial tilt of nearly 98 degrees. Earth is tilted by about 23.5 degrees relative to the plane of its orbit. Uranus is tilted so dramatically that it effectively rotates on its side. As the planet travels around the Sun, its poles can point almost directly toward or away from the Sun at certain parts of its orbit. This creates extraordinary seasons. Uranus takes about 84 Earth years to complete one journey around the Sun, so each season lasts roughly 21 Earth years. For long periods, one hemisphere can experience something close to continuous sunlight, while the other remains in prolonged darkness. Then, as Uranus continues around its orbit, those conditions slowly reverse. Exactly how the planet ended up tilted so severely remains uncertain. One leading idea is that Uranus suffered an enormous collision early in the history of the solar system. A sufficiently massive impact could have altered its rotation dramatically. Other models suggest the final tilt may have resulted from several large impacts, rather than one single catastrophic event. There are also more complicated possibilities involving gravitational interactions during the early rearrangement of the planets. The important point is that Uranus probably did not simply form in its present orientation without disturbance. Something significant happened to it. The planet also possesses rings. They are much darker and fainter than Saturn's, which is one reason they remained undiscovered for so long. In 1977, astronomers studying Uranus watched the planet pass in front of a distant star. This technique is called stellar occultation. The intention was to study Uranus itself by observing how the starlight changed as it passed behind the planet. But before Uranus covered the star, the light briefly dimmed several times. It dimmed again after the planet had passed. The pattern revealed narrow rings surrounding Uranus. The discovery was a reminder that ring systems are not unique to Saturn. Uranus also has an unusual magnetic environment. Its magnetic field is tilted strongly relative to its axis of rotation, and the magnetic field is significantly offset from the planet's centre. This produces a magnetosphere that is highly asymmetric. As Uranus rotates, the magnetic environment around it changes in a complicated way, creating a very different system from the more centrally organised magnetic fields of planets such as Earth. Much of what we know directly about Uranus comes from one brief encounter. Voyager 2 flew past the planet in January 1986. It remains the only spacecraft ever to visit Uranus at close range. During that encounter, Voyager 2 measured the atmosphere and magnetic field, photographed the rings, and observed several major moons. Among them are Miranda, Ariel, Umbriel, Titania, and Oberon. These moons are themselves complex worlds. Miranda contains extraordinary cliffs, ridges, fault systems, and patches of terrain that look as though the surface was broken apart and rearranged. Ariel shows valleys, fractures, and evidence of substantial geological modification. Titania and Oberon also preserve signs of large-scale tectonic activity. Some of these moons may even have experienced internal oceans at different stages of their histories, and the possibility that some could retain liquid layers today remains an area of scientific interest. Since Voyager 2, astronomers have continued studying Uranus from afar. The Hubble Space Telescope has tracked storms, clouds, and seasonal changes. The James Webb Space Telescope has revealed atmospheric details and the planet's faint rings in infrared light. Ground-based observatories have added further measurements of winds, storms, chemistry, and temperature. But there is a clear difference between watching Uranus from Earth and placing a spacecraft into orbit around it. Saturn has been studied for years by an orbiting spacecraft. Uranus has been visited once, during a rapid flyby several decades ago. That contrast tells us something important about the journey outward. Beyond Saturn, direct exploration becomes sparse very quickly. The distances grow. Travel times lengthen. Communication slows, solar power becomes less practical, and enormous worlds remain known from only a few hours of close observation. Uranus is not merely another planet on the way to the edge. It is the beginning of a region where our maps remain surprisingly incomplete. And farther out still waits Neptune, the last major planet and the final giant world before the planetary system gives way to the frozen populations beyond. Neptune has a particularly unusual place in the history of astronomy, because it was not simply found by looking into the sky. It was predicted. By the early 19th century, astronomers had become increasingly aware that the orbit of Uranus did not behave exactly as expected. Its position showed small deviations that could not be explained perfectly by the gravitational influence of the planets already known. One possibility was that another planet existed farther out, gently disturbing Uranus through gravity. Two mathematicians, Urbain Le Verrier in France and John Couch Adams in Britain, independently worked on the problem and calculated where such a planet might be found. In 1846, Johann Gottfried Galle and Heinrich Loewy de Rest observed the sky near the position predicted by Urbain Le Verrier. There was Neptune. It was one of the most remarkable demonstrations of gravitational theory in the history of astronomy. A planet billions of kilometres away had effectively announced its presence through the tiny influence it exerted on another world. Neptune orbits the Sun at an average distance of roughly 30 astronomical units, about 4.5 billion kilometres away. One journey around the Sun takes almost 165 Earth years. In fact, Neptune completed its first full orbit since its discovery only in the early 21st century. Like Uranus, Neptune is classified as an ice giant. Its atmosphere is dominated by hydrogen and helium, with methane contributing to its blue appearance by absorbing red wavelengths of sunlight. But beneath the atmosphere lies a much denser interior containing larger proportions of substances such as water, ammonia, methane, and heavier material under enormous pressures and temperatures. Calling these substances ices refers mainly to their chemical role in the formation of the outer planets. Deep inside Neptune, they would not resemble the neat frozen cubes we normally imagine when we hear the word ice. From a distance, Neptune can appear calm and beautifully blue. Up close, it is anything but calm. When Voyager 2 passed the planet in 1989, it observed an enormous storm system known as the Great Dark Spot. The feature was comparable in scale to Earth. Voyager also recorded bright clouds, rapidly changing atmospheric structures, and winds travelling at extraordinary speeds. Some winds on Neptune can exceed 2,000 kilometers per hour. That makes them among the fastest measured anywhere in the solar system. The strange part is how little sunlight Neptune receives. At 30 astronomical units from the Sun, the planet receives only a tiny fraction of the solar energy reaching Earth. It might seem reasonable to expect such a distant atmosphere to be sluggish. Instead, Neptune has powerful storms and extremely fast winds. Part of the explanation appears to come from inside the planet. Neptune emits significantly more energy than it receives from the Sun. Heat escaping from its interior contributes to atmospheric motion and helps drive circulation. This is an important reminder that planetary weather does not always depend mainly on sunlight. A planet can carry its own reservoir of internal energy, and that energy can continue shaping the atmosphere billions of kilometers from the Sun. Neptune also has rings. They are faint, narrow, and dusty, compared with the spectacular rings of Saturn. Some regions appear brighter than others, producing unusual concentrations called ring arcs. Instead of material being distributed evenly around an entire ring, particles can become concentrated into particular regions through gravitational interactions. Neptune's moons also influence this environment. The most important of them is Triton, a large moon whose unusual orbit suggests that it was probably captured rather than formed alongside Neptune in the ordinary way. Voyager 2 remains the only spacecraft ever to visit Neptune at close range. Its flyby in August 1989 completed the spacecraft's grand tour of the giant planets. After visiting Jupiter, Saturn, Uranus, and finally Neptune, Voyager 2 continued outward on a trajectory that would eventually carry it beyond the heliosphere. That brief encounter remains our only close view of the most distant major planet. Everything since then has been studied from much farther away. And yet Neptune influences a region far beyond its own atmosphere and moons. Its gravity plays an important role in organising the Kuiper Belt. Many icy bodies beyond Neptune occupy orbital resonances with the planet. An orbital resonance occurs when two objects complete their orbits in a repeating numerical relationship. Pluto provides the most famous example. For every 3 orbits Neptune completes around the Sun, Pluto completes roughly 2. This 3-to-2 resonance keeps their movements organised in such a way that, despite Pluto's orbit crossing inside the distance of Neptune's at certain points, the two worlds do not come dangerously close. Neptune has shaped many other distant objects in similar ways. Its gravity helped scatter bodies outward during the early history of the solar system, captured others into resonances, and contributed to the complex architecture that exists beyond the major planets today. So Neptune can reasonably be called the end of the planetary solar system. There are no recognized major planets beyond it. But it is not the end of the solar system itself. Beyond Neptune are dwarf planets, icy worlds, scattered objects, comets, and populations extending across billions upon billions of kilometers. The character of exploration changes here. Closer to the Sun, we can visit planets and photograph entire worlds. Beyond Neptune, much of the structure has to be reconstructed from faint points of light, slow movements against background stars, gravitational relationships, and the occasional spacecraft travelling through an almost unimaginable emptiness. Neptune is therefore less like a wall at the edge of the solar system, and more like the final lighthouse before a much wider ocean. The major planets end here. The solar system does not. Triton is one of the clearest signs that the outer solar system has not always been arranged the way we see it today. It is Neptune's largest moon, discovered by William Lassell in 1846, only a few weeks after Neptune itself was identified. At first glance, Triton might seem like an ordinary large moon orbiting an outer planet, but its motion immediately tells us otherwise. Triton travels around Neptune in a retrograde orbit. That means it moves in the opposite direction to Neptune's rotation. Most large moons orbit their planets in the same general direction that the planets rotate, because they formed from material moving together in a disk around the young planet. Triton does not fit that pattern. Its backward orbit is strong evidence that it did not form around Neptune in the usual way. Instead, Triton was probably captured. Before that happened, it may have been a trans-Neptunian object, part of the broader population of icy worlds beyond Neptune. One leading idea is that Triton originally belonged to a binary system, meaning two objects orbiting one another. If that pair passed close to Neptune, the planet's gravity could have disrupted the system. One object may have been thrown away while Triton lost enough energy to remain bound to Neptune. That capture would have been violent in gravitational terms. Triton's original orbit was probably far more elongated than it is today, and as it gradually settled into a more circular path, enormous amounts of orbital energy would have been converted into heat. The event may also have disrupted Neptune's original system of moons. Existing satellites could have been scattered, collided with one another, or been destroyed, with some of the present smaller moons forming later from the debris. Triton therefore may be less like a moon born around Neptune, and more like a captured world that reshaped the entire system around it. Its surface strengthens that impression. Triton is one of the coldest known large bodies in the solar system. Temperatures near the surface can fall to around 235 degrees below 0 Celsius. Frozen nitrogen covers large areas, along with water ice, carbon dioxide ice, and other volatile materials. Yet despite the cold, Voyager 2 found a surface that looked unexpectedly active. When the spacecraft passed Triton in 1989, it revealed smooth plains, long faults, relatively few impact craters, and strange textured regions sometimes described as cantaloupe terrain. The lack of heavy cratering across much of the surface suggests that parts of Triton have been resurfaced relatively recently in geological terms. Even more surprising were dark streaks associated with active geysers. Voyager 2 observed plumes of nitrogen gas and dark particles rising several kilometers above the surface before being carried sideways by the thin atmosphere. These eruptions are thought to be powered largely by weak sunlight passing through translucent nitrogen ice and warming darker material beneath it. Gas pressure then builds until material escapes through the surface. Even at Neptune's distance from the Sun, faint sunlight can still drive active processes. Triton may also hide something deeper. Its internal composition, past tidal heating, and evidence of geological activity have led scientists to consider the possibility of a buried liquid water ocean beneath the frozen crust. That remains uncertain. No spacecraft has directly detected such an ocean, and Triton has not been revisited since Voyager 2. But the possibility is scientifically plausible enough to make the Moon an important target for future exploration. Saturn's story is also unfinished. Because it orbits Neptune in the opposite direction to the planet's rotation, tidal interactions are gradually stealing orbital energy from the Moon. Very slowly, Saturn is spiralling inward. Over billions of years, it may eventually approach Neptune's Roche limit, where tidal forces could become strong enough to break it apart. If that happens, Saturn could one day contribute material to a spectacular new ring system around Neptune. For now, though, it remains intact, and its real importance lies in what it tells us about the territory beyond Neptune. Triton may be a captured member of the same broad family of icy worlds that populates the outer solar system. In that sense, it is a preview. Before we even leave the final major planet behind, Neptune is already carrying a piece of the distant frontier around with it. For much of the 20th century, Pluto seemed to offer a wonderfully simple ending to the planetary solar system. It was discovered in 1930 by Clyde Tombaugh, a young astronomer working at Lowell Observatory in Arizona. Tombaugh had been comparing photographs of the night sky, searching for a faint object that moved against the background stars. When he found Pluto, it was quickly accepted as the 9th planet. For decades, school children learned the solar system as a sequence ending neatly with Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune, and finally Pluto. But Pluto was always an unusual member of that list. It is tiny compared with the 8 major planets. Its diameter is only about 2,370 kilometers, making it considerably smaller than Earth's moon. Its orbit is also much more eccentric than those of the major planets. Instead of remaining at roughly the same distance from the Sun throughout its journey, Pluto moves between about 30 and nearly 50 astronomical units away. Its orbital plane is also strongly inclined compared with the relatively flat arrangement followed by the major planets. For part of each orbit, Pluto actually travels closer to the Sun than Neptune does. That sounds as though the two worlds should occasionally risk a collision. They do not. Pluto and Neptune are locked into a gravitational relationship known as a 3-to-2 orbital resonance. For every 3 orbits completed by Neptune, Pluto completes roughly 2. Their motions are synchronized in such a way that when Pluto passes through the part of its orbit that lies inside Neptune's average distance from the Sun, Neptune is safely positioned elsewhere. This resonance has remained stable for immense periods of time. Pluto was strange, but for many years it still seemed unique. Then astronomers began finding more objects beyond Neptune. Some were large enough to complicate the old picture considerably. Haumea and Makemake were discovered in the outer solar system, along with many other trans-Neptunian objects. Then came Eris. Eris is similar to Pluto in overall scale, and was initially thought to be slightly larger. Its discovery created an awkward question. If Pluto was a planet, should Eris be a planet as well? And if Eris qualified, how many more worlds might eventually need to be added? The issue forced astronomers to reconsider what the word planet was actually supposed to mean. In 2006, the International Astronomical Union adopted a formal definition for planets in the solar system. Under that definition, a planet must orbit the Sun, be massive enough for its own gravity to pull it into a nearly round shape, and have cleared the neighbourhood around its orbit. Pluto meets the first 2 conditions. It does not meet the third. Its orbital region contains many other objects, and Pluto is part of a much broader population rather than gravitationally dominating its surroundings in the way Earth or Neptune does. Pluto was therefore classified as a dwarf planet. That decision became surprisingly emotional for something involving a frozen world billions of kilometres away. But scientifically, the change reflected an important improvement in our understanding. Pluto had not physically changed. The solar system had, or rather our knowledge of it had. Instead of one isolated ninth planet beyond Neptune, astronomers had discovered an entire population of icy worlds. Pluto was no longer an odd object sitting alone near the edge. It was one important member of the Kuiper Belt. And Pluto itself turned out to be far more interesting than the old planetary diagrams had suggested. The National Aeronautics and Space Administration spacecraft New Horizons flew past Pluto in July 2015. Before that encounter, even the best images showed Pluto as a small, blurred world. New Horizons transformed it into a landscape. The spacecraft revealed towering mountains made largely from water ice, broad plains of frozen nitrogen, layered atmospheric haze, possible cryovolcanic structures, and terrain that appeared surprisingly young. One of its most striking features is Sputnik Planitia, the bright heart-shaped region visible in many images of Pluto. Much of Sputnik Planitia is filled with nitrogen ice. The surface is divided into broad cells that appear to be created by slow convection. Relatively warmer nitrogen ice rises from below, spreads, cools, and eventually sinks again. This process continually renews parts of the surface and helps explain why some areas contain very few impact craters. Pluto is not simply an ancient frozen object that stopped changing billions of years ago. It has active geology. It has a thin atmosphere, mainly composed of nitrogen with smaller amounts of methane and carbon monoxide. As Pluto moves closer to and farther from the Sun, atmospheric gases can freeze onto the surface and later return to the atmosphere. Pluto also has 5 known moons. The largest, Charon, is unusually large compared with Pluto itself. Charon is more than half Pluto's diameter. The two objects orbit a common centre of mass that lies outside Pluto's surface. For that reason, Pluto and Charon are sometimes described as behaving rather like a binary system. They continually face the same sides toward one another, locked together by tidal forces, while the smaller moons orbit farther out. Everything about Pluto therefore weakens the idea that the solar system should have a neat planetary ending. Its orbit does not define a fixed boundary. At some points Pluto is near 30 astronomical units from the Sun, while at others it approaches 50. And even at its most distant point, many known objects continue far beyond it. The old map ended with Pluto, because Pluto was once the last large world we knew. The modern map does not end there at all. Beyond Neptune, named planets begin to give way to populations. Instead of travelling from one major world to another, we enter a broad region filled with dwarf planets, icy bodies, resonant objects, binaries, fragments, and ancient remnants of planetary formation. Pluto did not become less important when it stopped being called the 9th planet. In many ways it became more useful. It showed us that the apparent edge of the planetary system was not an edge at all. It was the entrance to the Kuiper Belt. For a long time, Pluto seemed almost alone beyond Neptune. That picture changed dramatically in the late 20th century. Astronomers had already suspected that more objects might be waiting in the distant outer solar system. Kenneth Edgeworth had discussed the possibility of a population of small bodies beyond Neptune, and Gerard Kuiper later considered how material in this region might have behaved during the early history of the solar system. But the modern Kuiper Belt is more complicated than either astronomer originally imagined. The breakthrough came in 1992, when David Jewett and Jane Liu discovered a distant object beyond Pluto and Charon. That object, later named Albion, was the first recognized member of a much larger population of trans-Neptunian worlds. Suddenly, Pluto no longer looked like an isolated oddity. it looked like part of a system. The Kuiper Belt is a broad, donut-shaped region beginning near the orbit of Neptune and extending outward through much of the space between roughly 30 and 50 or 55 astronomical units from the Sun. It is sometimes compared with the asteroid belt between Mars and Jupiter, but the comparison can be misleading. The Kuiper Belt is vastly larger. It is also much colder. And while the asteroid belt contains many rocky and metallic bodies, Kuiper Belt objects often contain substantial amounts of frozen water, methane, ammonia, and other volatile substances. These are remnants from the formation of the solar system, preserved in deep cold for billions of years. The region is not one uniform ring. Different groups of objects occupy different kinds of orbits. Some belong to what astronomers call the classical Kuiper Belt. Within this population are dynamically cold and dynamically hot objects. Those terms have nothing to do with their actual temperatures. Almost everything out there is extremely cold. Instead, cold and hot describe the shapes and orientations of the orbits. Dynamically cold objects tend to follow more circular paths with relatively small inclinations to the main plane of the solar system. Dynamically hot objects generally have more tilted and eccentric orbits, suggesting a more disturbed history. Neptune is responsible for much of this structure. Its gravity does not simply affect nearby objects randomly. Many Kuiper Belt bodies occupy orbital resonances with Neptune. Pluto belongs to the best-known group. Objects in the same 3:2 resonance as Pluto are often called Plutinos. For every 3 orbits Neptune completes, a Plutino completes approximately 2. This repeated relationship prevents dangerous close encounters while creating long-term orbital stability. Other groups occupy different resonances, forming patterns that preserve evidence of how Neptune moved through the early solar system. Farther out and on more disturbed paths lies the scattered disk. Objects there often have highly eccentric orbits, carrying them from regions relatively close to Neptune to enormous distances farther away. Many appear to have been scattered by gravitational encounters with Neptune, especially during the chaotic early history of the outer planets. The worlds found throughout this region are surprisingly diverse. Pluto has glaciers, mountains, haze, and a complex atmosphere. Haumea rotates extraordinarily quickly and has an elongated shape. Makemake is a bright, icy dwarf planet. Quow has a large moon and an unusual ring lying surprisingly far from its surface. Orcus occupies an orbit that has some similarities to Pluto's, although the two remain positioned very differently. And these are only the larger, easier objects to detect. Thousands of trans-Neptunian objects have been catalogued, but astronomers believe the actual population is vastly greater. Smaller bodies are extraordinarily difficult to see. They are far from the Sun, so they receive very little sunlight. They reflect only a small amount of that light back toward Earth. And against the immense background of distant stars, many move so slowly that identifying them requires repeated observations over long periods. The Kuiper Belt has also been shaped by collisions. Over billions of years, icy bodies have struck one another, producing fragments, moons, dust, and families of objects, sharing similar compositions and orbital histories. Some binary systems may preserve clues about gentler interactions from much earlier times. Others record violent events. To understand why the Kuiper Belt looks this way, scientists have had to reconstruct the early movement of the giant planets. One influential explanation is the Nice model, named after the city of Nice in France. In this model, Jupiter, Saturn, Uranus and Neptune did not remain exactly where they formed. Instead, their orbits changed over time. The giant planets exchanged gravitational energy with one another and with enormous populations of smaller bodies. Neptune migrated outward. As it moved, its gravity swept through the distant disk of icy objects. Some bodies were captured into resonances. Others were scattered inward or outward. Many were removed from the region entirely. This process could explain why the Kuiper Belt contains such a complicated mixture of stable, resonant, inclined, eccentric, and scattered populations. It also suggests that the belt we see today is only a surviving remnant of something that was once much more massive. That makes the Kuiper Belt valuable for more than simply mapping the outer solar system. It is an archaeological record. Its objects preserve evidence of planetary migration, collisions, orbital disruption, and the earliest stages of solar system formation. But despite its enormous scale, the Kuiper Belt still does not give us a clean outer edge. Beyond its main populations, objects continue onto more distant and more extreme orbits, and even after the visible family of icy worlds begins to thin out, the influence of the Sun continues much farther. The Kuiper Belt may feel like the frontier, but the frontier itself keeps moving outward. Beyond the main Kuiper Belt, the solar system does not suddenly become empty. Instead, the neatness begins to disappear. The broad population of icy bodies beyond Neptune gradually gives way to objects travelling on increasingly stretched, tilted, and distant orbits. There is no clean outer wall where the Kuiper Belt ends and something completely different begins. The structure simply becomes more scattered. One important population is known as the scattered disk. Its members are thought to have been strongly influenced by Neptune, particularly during the early history of the solar system when the giant planets were still changing their orbits. Close gravitational encounters with Neptune could give smaller bodies enormous kicks. Some were pushed inward. Some were thrown out of the solar system altogether. Others survived on highly eccentric and inclined paths that carry them far beyond the main Kuiper Belt. Eris is one of the best known examples. Its discovery was announced in 2005 and played a major role in the debate over what should count as a planet. Eris is similar in overall scale to Pluto, but its orbit is much more distant and elongated. At its closest, it remains well beyond Neptune. At its most distant, it travels to roughly 100 astronomical units from the Sun. Its existence helped reveal that Pluto was not a lone object sitting near the edge of the known planetary system. There were other substantial worlds scattered throughout this distant region. But even the scattered disk does not contain all of the strange objects found beyond Neptune. Some worlds appear almost detached from the known planets. A detached object follows an orbit whose closest approach to the Sun is so distant that Neptune cannot easily explain its present motion through ordinary repeated encounters. That creates a puzzle. If Neptune is too far away to disturb these objects strongly today, what placed them on such unusual orbits? Sedna is the most famous example. Sedna was discovered in 2003 by a team including Michael Brown, Chad Trujillo, and David Rabinowitz. Its orbit is extraordinary. Even at its closest approach to the Sun, Sedna remains around 76 astronomical units away. At its most distant, it travels many hundreds of astronomical units from the Sun. One complete orbit takes roughly 11,000 years. For almost all of that time, Sedna is unimaginably remote. Its closest point is already far beyond Neptune's reach compared with most scattered objects. That has made its orbit particularly difficult to explain. Several possibilities have been proposed. One idea reaches back to the birth of the Sun itself. The Sun probably formed alongside many other stars inside a stellar nursery or birth cluster. If another young star passed relatively close to the early solar system, its gravity could have disturbed distant icy bodies and lifted their orbits away from the region controlled by Neptune. Those ancient encounters may have left signatures that survive even today. Another possibility involves the early migration of the giant planets. When Jupiter, Saturn, Uranus and Neptune were moving through the young solar system, their gravitational interactions may have produced configurations capable of sending objects into unusually distant orbits. At still greater distances, the gravitational field of the Milky Way can also become relevant. Galactic tides are extremely weak across ordinary planetary distances, but over immense spans of space and very long periods of time, they can gradually alter the orbits of objects only loosely attached to the Sun. And then there is the possibility that something large remains undiscovered. In 2016, Konstantin Batygin and Michael Brown proposed what became known as the Planet 9 hypothesis. They argued that certain extremely distant trans-Neptunian objects appeared to have orbital orientations that were not randomly distributed. One possible explanation was the gravitational influence of a large planet orbiting far beyond Neptune. In many versions of the hypothesis, this hypothetical world would have several times the mass of Earth and follow a large, elongated orbit, hundreds of astronomical units from the Sun. Such a planet could, in principle, gravitationally organize the paths of smaller distant bodies. But Planet 9 has never been directly observed. That point matters. It remains a hypothesis, not a discovered planet. Astronomers continue debating whether the apparent clustering of distant orbits is genuinely caused by an unseen massive object. The sample of known distant bodies is still small. Observational surveys do not examine every part of the sky equally. Some regions are easier to search than others, and some types of orbit make objects more likely to be discovered. These selection effects can create patterns that look physically meaningful, even when part of the pattern comes from the way observations were made. Alternative dynamical explanations have also been proposed. More discoveries are needed before the question can be settled. Finding those objects is exceptionally difficult. A world hundreds of astronomical units away receives very little sunlight. The sunlight that does reach it must then reflect from its surface and travel all the way back toward telescopes near Earth. The result is an extremely faint point of light. Distance also makes apparent motion painfully slow. A nearby asteroid can visibly shift against the background stars over a relatively short observing period. A distant trans-Neptunian object may creep across the sky so gradually that astronomers need repeated images separated by substantial periods of time to recognize the movement. Large astronomical surveys therefore collect enormous numbers of images and search them for tiny changes. The National Aeronautics and Space Administration funded Backyard Worlds project has involved members of the public in examining wide-field observations for faint-moving objects, particularly nearby brown dwarfs and possible distant solar system bodies. Professional surveys use increasingly powerful cameras, automated processing, and long-term observations to perform similar searches across vast areas of sky. Yet our map remains incomplete. This is partly why the scattered disk and detached populations are so important. They occupy an uncertain region between the comparatively familiar Kuiper Belt and something much more distant. Some detached objects may represent an intermediate population leading toward the inner portion of the Oort Cloud. Others may have completely different histories. The categories themselves can become blurred because the outer solar system is not divided into perfectly separated shells. The farther we travel from the planets, the less useful the picture of tidy concentric rings becomes. Instead, there are overlapping populations. Some were scattered by Neptune, some were trapped into resonances, some may preserve evidence of stellar encounters billions of years ago. Some travel so far outward that the wider galaxy begins to influence them. And somewhere among these faint, slowly moving worlds may still be objects large enough to change our understanding of the solar system again. The edge is becoming harder to draw because the solar system itself is becoming less orderly. What began as a row of planets has dissolved into an enormous gravitational landscape, filled with remnants whose strange orbits preserve the history of events that happened when the sun was still young. For most of human history, the Kuiper Belt could only be studied from a distance. Its worlds were points of light moving slowly against the stars, their surfaces hidden across billions of kilometers of space. New Horizons changed that. The mission was created by the National Aeronautics and Space Administration to explore Pluto and then continue into the wider Kuiper Belt, becoming the first spacecraft designed specifically to examine this distant population at close range. The spacecraft was developed and is operated by the Johns Hopkins University Applied Physics Laboratory, working with the Southwest Research Institute. Alan Stern serves as the mission's principal investigator. New Horizons launched in January 2006. Reaching Pluto directly would have required an extremely long journey, so the spacecraft followed a carefully designed path past Jupiter. In 2007, it flew through the Jovian system and used Jupiter's gravity to increase its speed. This gravity assist shortened the journey to Pluto by several years. Even with that help, New Horizons still spent about 9.5 years travelling through space before reaching its primary destination. During most of that time, there was very little scenery. The spacecraft crossed enormous stretches of the outer solar system, with the planets growing increasingly distant behind it and sunlight steadily weakening. Then, in July 2015, Pluto stopped being a distant blur. New Horizons passed within roughly 12,500 kilometers of its surface. The encounter happened quickly. Because the spacecraft was travelling at many kilometers per second and was not slowing down to enter orbit, the most important observations had to be collected during a narrow window surrounding the flyby. New Horizons was effectively racing past an unexplored world while turning its instruments toward carefully selected targets. It photographed the surface, it measured the atmosphere, it studied Pluto's moons, it examined temperatures, composition, geology, and escaping gases, and then it continued onward. Because Pluto was billions of kilometers from Earth, New Horizons could not simply send all of its information home immediately. Radio signals took hours to cross the distance. The spacecraft stored its observations and transmitted them gradually through the deep space network. The complete return of the flyby data took more than a year. What arrived completely changed the image of Pluto. Instead of an ancient, uniformly cratered frozen world, scientists saw landscapes that appeared surprisingly active. There were mountains several kilometers high made largely from water ice. There were extensive deposits of frozen nitrogen. There were layers of atmospheric haze rising above the surface. There were signs of glacial movement, varied surface chemistry, and terrain that had been renewed relatively recently in geological terms. Some large features have also been interpreted as possible cryovolcanoes, structures formed when icy material or other volatile substances rise from the interior rather than molten rock erupting as they would in ordinary terrestrial volcanism. The most famous region, Sputnik Planitia, revealed broad expanses of nitrogen ice divided into enormous cells. These patterns are consistent with slow convection within the ice, showing that even at Pluto's extraordinary distance from the Sun, the surface can continue to evolve. But Pluto was not the end of the mission. New Horizons was already travelling through the Kuiper Belt, and astronomers began searching for another object lying close enough to the spacecraft's trajectory to permit a second encounter. They found one. On the first day of 2019, New Horizons flew past Arrokoth. The encounter took place more than 6 billion kilometres from the Sun. Arrokoth is dramatically smaller than Pluto, only a few tens of kilometres long, but in some respects that made it even more valuable. It has two distinct lobes joined together, producing what astronomers call a contact binary. Rather than appearing to have formed through a violent high-speed collision, its shape suggests that two separate objects approached one another comparatively gently before becoming permanently joined. That seemingly modest detail reaches back more than 4.5 billion years. During the formation of the solar system, tiny particles gradually assembled into larger bodies. Exactly how those objects grew into planetesimals, and eventually into planets, remains an important question. Arrokoth appears to preserve evidence of a relatively gentle form of assembly in which nearby bodies formed within the same region lost relative speed and gradually came together. Unlike larger planets and moons, Arrokoth has not been strongly transformed by internal heat. It has not developed a substantial atmosphere. It has not experienced the extensive geological recycling found on larger worlds. And its remote location means it has remained comparatively isolated from many of the processes that dramatically altered objects closer to the Sun. It is therefore something close to a preserved sample from the solar system's earliest construction. New Horizons did not simply photograph it. Measurements of its shape, surface colour, composition, cratering and geology provided clues about how primitive bodies formed within the outer protoplanetary disk. The spacecraft has also studied other Kuiper Belt objects from a distance, and measured the dust environment through which it travels. These observations help scientists estimate how much small material exists in regions that are almost impossible to examine directly from Earth. But there is an important distinction between travelling through the Kuiper Belt and crossing a precise edge. The Kuiper Belt does not end like a coastline. Its populations gradually thin. Different classes of objects occupy different distances and different kinds of orbit. Some remain within the classical belt. Some are controlled by resonances with Neptune. Others belong to the scattered disk and travel far beyond the main concentration of objects. So there is no moment when New Horizons can pass a sign announcing that the Kuiper Belt has officially ended. The spacecraft simply travels into regions where the known population becomes increasingly sparse. Operating anything at these distances is extraordinarily difficult. Sunlight is too weak for conventional solar panels to provide practical power, so New Horizons relies on a radioisotope power source. Communication becomes slower with every kilometre travelled. Radio signals now require many hours to cross the distance between the spacecraft and Earth. Commands must therefore be prepared long before anyone can know the result. Navigation is similarly unforgiving. At billions of kilometres from Earth, a tiny error in direction can become a very large miss by the time a spacecraft reaches its target. There is no real-time correction from a person holding a joystick. Everything depends on careful planning, precise navigation, autonomous spacecraft systems, and patience. New Horizons has shown us that the Kuiper Belt is not merely a distant collection of frozen debris. It contains complex worlds and remarkably well-preserved remnants of planetary formation. Pluto revealed active geology. Arrokoth revealed something closer to the raw material from which worlds were assembled. And beyond these objects, the spacecraft continues into a part of the solar system where solid worlds become increasingly sparse, and another kind of structure becomes more important. Even where there are fewer planets, moons, and icy bodies to see, the Sun is still creating an enormous invisible environment around them all. The Sun does much more than illuminate the solar system. It also fills the space around it with matter. Every second, enormous numbers of charged particles stream away from the Sun in all directions. Most are protons and electrons, moving outward at hundreds of kilometers per second. This continuous flow is called the solar wind. Long before spacecraft could measure it directly, Eugene Parker argued in the 1950s that the Sun's outer atmosphere could not remain perfectly static. The extremely hot corona should expand outward into space. Parker's calculations predicted a persistent supersonic stream of charged particles leaving the Sun. At first, the idea was controversial. Space was still often imagined as almost completely empty. But early spacecraft measurements confirmed that the solar wind was real. The Sun was not sitting quietly at the center of a vacuum. It was constantly breathing material into the solar system. As the solar wind moves outward, it carries more than particles. It also carries the Sun's magnetic field. Because the Sun rotates, those magnetic field lines become stretched and twisted into an enormous spiral pattern through space. The result is a vast region around the Sun, known as the heliosphere. The heliosphere surrounds all the major planets. Earth is inside it. Saturn is inside it. Neptune is inside it. The Kuiper Belt lies within much of it as well. But the heliosphere should not be confused with the complete gravitational solar system. They are defined by different things. An object belongs gravitationally to the solar system if it remains bound to the Sun through gravity. The heliosphere, by contrast, is defined by the behavior of plasma, magnetic fields, and pressure. A spacecraft can leave the heliosphere while still remaining strongly affected by the Sun's gravity. That distinction becomes extremely important when we ask where the solar system ends. The solar wind is also far from uniform. Its speed changes, its density changes, its magnetic structure changes. Different regions of the Sun can produce faster or slower streams. The Sun's roughly 11-year activity cycle alters its magnetic field and changes the conditions flowing outward. Solar eruptions can throw enormous clouds of plasma into space. These events, known as coronal mass ejections, can disturb the solar wind and create large changes in the magnetic environment across the solar system. Near Earth, these disturbances can produce geomagnetic storms and auroras. Farther away, their influence spreads into an enormous bubble billions of kilometers across. Eventually, however, the solar wind begins to lose the contest. The space between stars is not truly empty. It contains the interstellar medium. This is an extremely thin mixture of neutral gas, charged plasma, dust grains, energetic particles, and magnetic fields. Compared with Earth's atmosphere, it is almost unimaginably sparse. But over enormous distances, even this faint material exerts pressure. The heliosphere exists because the outward pressure of the solar wind pushes against the surrounding interstellar environment. Closer to the Sun, the solar wind dominates. Farther away, the balance begins to change. One of the first major boundaries is called the termination shock. Until this point, much of the solar wind has been moving faster than the speed at which pressure disturbances can travel through the plasma. In that sense, the flow is supersonic. At the termination shock, pressure from the surrounding interstellar environment forces the solar wind to slow abruptly. It becomes subsonic. The particles do not stop. They continue moving outward, but now they are slower, hotter, and more compressed. Beyond the termination shock lies a region called the heliosheath. This is the outer layer of the heliosphere. The solar wind has been slowed and disturbed here, and the plasma becomes increasingly turbulent as it approaches the boundary with interstellar space. The heliosheath is not a calm shell. It is a complicated region where charged particles, magnetic fields, and pressure interact across enormous distances. Eventually comes the heliopause. This is the boundary where the outward influence of the solar wind is balanced by the surrounding interstellar environment. Beyond it, the plasma is no longer dominated by material flowing directly outward from the Sun. The heliopause is therefore one of the strongest candidates for what we might call an edge of the solar system. But it is not shaped like a perfect glass bubble. The heliosphere changes. Solar activity varies with time. The surrounding interstellar medium is not perfectly uniform. The Sun itself is moving through the Milky Way, carrying the heliosphere with it. All of these factors affect the pressure balance. For many years, the heliosphere was often pictured rather like a comet, with a rounded region facing the direction of the Sun's motion and a very long tail extending behind it. Modern models and observations suggest that the true geometry may be more complicated. Different models produce shapes ranging from stretched structures to more compact forms with broad lobes. The important point is that there is no perfectly smooth spherical wall surrounding the Sun. The heliosphere is dynamic. It responds to both the Sun and the environment through which the solar system is travelling. It also offers us some protection. Galactic cosmic rays are extremely energetic particles arriving from outside the solar system. Some originate from violent processes elsewhere in the Milky Way, including supernova remnants and other high-energy environments. The magnetic fields and charged particles of the heliosphere can deflect or reduce some of these incoming particles. The protection is not complete. Cosmic rays still reach Earth and the other planets, but conditions inside the heliosphere are different from those outside it. In that sense, the Sun creates an enormous environmental bubble around its planetary family. Nothing about this boundary can be seen in the way we see the surface of a planet. There is no glowing wall in the darkness. No obvious line appears in photographs. To detect the heliosphere's outer regions, spacecraft must measure particles, plasma density, magnetic fields, and energetic radiation. The farther outward we travel, the less the solar system resembles a collection of visible worlds. Its boundaries become invisible. They are revealed not by what we can see, but by changes in the behavior of matter itself, and eventually a spacecraft can cross one of those invisible boundaries and find that the particles surrounding it no longer belong mainly to the Sun. At that point, in one very specific and scientifically meaningful sense, interstellar space has begun. There is a point, far beyond Neptune and far beyond the main Kuiper Belt, where the Sun's influence changes in a very specific way. This boundary is called the heliopause. It marks the outer edge of the heliosphere, the enormous region filled and shaped by the solar wind. Inside the heliopause, the space environment is still dominated by particles and magnetic fields carried outward from the Sun. Beyond it, the surrounding interstellar plasma becomes dominant. The boundary is invisible. There is no wall, no surface, and no sudden change in scenery. A spacecraft crossing it would not see a line pass beneath it. Instead, the evidence appears in measurements. Particle populations change. Plasma density changes. Magnetic conditions change, and the two spacecraft that have measured this transition directly are Voyager 1 and Voyager 2. Both were launched by the National Aeronautics and Space Administration in 1977. Their original purpose was planetary exploration. Voyager 1 travelled past Jupiter and Saturn. Voyager 2 continued farther, becoming the only spacecraft ever to visit Uranus and Neptune at close range. After those encounters, both spacecraft continued outward. Their planetary missions gradually became interstellar missions, For decades, Edward Stone served as Voyager project scientist, helping guide the interpretation of measurements arriving from increasingly distant parts of the solar system. The Jet Propulsion Laboratory has managed the mission, while communication has depended on the Deep Space Network, a global system of enormous radio antennas capable of detecting extraordinarily weak signals from deep space. By the early 21st century, Voyager 1 was approaching an environment that no functioning spacecraft had ever sampled directly. In 2004, it crossed the termination shock. This is the region where the solar wind, previously travelling outward at supersonic speed, slows sharply after encountering pressure from the surrounding interstellar medium. Voyager 1 then entered the heliosheath. For years it travelled through this turbulent outer region of the heliosphere. Scientists knew that the heliopause should lie farther ahead, but there was no simple marker announcing exactly where it would be. Then, in August 2012, Voyager 1 recorded a major change. The number of energetic particles associated with the heliosphere fell sharply. At almost the same time, the spacecraft detected an increase in galactic cosmic rays arriving from outside the heliosphere. Something fundamental about the surrounding environment had changed. The evidence became stronger when Voyager 1's plasma wave instrument detected oscillations associated with a denser plasma than that typically found inside the heliosphere. The spacecraft's direct plasma instrument had stopped functioning many years earlier, so scientists could not simply measure the surrounding plasma in the most straightforward way. Instead, they used the frequency of plasma waves to infer the density. Those measurements showed that Voyager 1 had entered the denser interstellar plasma beyond the heliopause. The conclusion became clear. Voyager 1 had entered interstellar space. Its crossing occurred at a distance of roughly 120 astronomical units from the Sun. That is around 4 times Neptune's average distance. 6 years later, Voyager 2 followed. Voyager 2 had crossed the termination shock in 2007. It then travelled through its own section of the heliosheath before reaching the heliopause in November 2018. Its crossing occurred at a slightly different distance and along a different direction from the Sun. This was scientifically valuable because the heliopause is not expected to be a perfectly spherical boundary. The Sun is moving through the surrounding interstellar medium. Solar activity changes over time. The pressure of the solar wind varies. The local interstellar environment is also not perfectly uniform. As a result, the heliopause can sit at different distances in different directions and can shift as conditions change. Voyager 2 provided another advantage. Unlike Voyager 1, its plasma instrument was still operating when it crossed the boundary. This allowed the spacecraft to measure the plasma directly. The data showed a transition from the thinner, hotter plasma associated with the outer heliosphere into the denser interstellar plasma beyond it. Together, the 2 Voyager crossings gave scientists the first direct measurements of the Sun's outer plasma boundary from 2 different locations. And yet the phrase interstellar space can easily create the wrong impression. Voyager 1 and Voyager 2 have entered interstellar space in the sense that they are outside the heliosphere. They are no longer travelling through plasma dominated by the solar wind. But they have not escaped the Sun's gravitational influence in any absolute sense. They are also nowhere near the probable outer gravitational boundary of the solar system. The distinction matters. The heliopause defines the edge of the Sun's solar wind environment. It does not define the outermost distance at which objects can remain gravitationally bound to the Sun. That more distant frontier may lie thousands of times farther away. The Voyagers themselves continue travelling outward at remarkable speeds, but even those speeds become modest when compared with the distances between stars. Neither spacecraft is heading toward a close encounter with another star anytime soon. Their journeys through interstellar space will continue for tens of thousands of years before they pass anywhere relatively near another stellar system. Communication with them is already difficult. Radio signals take many hours to travel between Earth and the spacecraft. By the time engineers transmit a command and receive confirmation that it has been carried out, much of a day can pass. Their electrical power also continues to decline. Both spacecraft rely on radioisotope generators, which convert heat from the natural radioactive decay of plutonium into electricity. As that heat source slowly weakens and the spacecraft systems age, engineers have had to switch off instruments and heaters to conserve power. The mission has become an exercise in careful survival. Every remaining watt matters. Despite that practical reality, both spacecraft carry something designed for a timescale far beyond their electronics. Attached to each Voyager is a golden record. The records contain sounds, images, music, greetings, and information intended to represent something of Earth and humanity. They were never expected to reach another civilization in any foreseeable future. Their real significance is symbolic. Long after the spacecraft fall silent, the records may continue drifting through the Milky Way. The Voyager missions have therefore crossed one genuine edge of the solar system. They have left the Sun's solar wind bubble and entered the interstellar environment beyond it. But the heliopause answers only one version of the original question. The Sun's particles may have largely given way to interstellar plasma. Its gravity has not. And somewhere much farther out, enormous populations of objects may still be orbiting the same star the Voyagers left behind. There is something slightly confusing about the way we talk about the Voyager spacecraft. Voyager 1 and Voyager 2 are often described as interstellar travelers. That is true. Both spacecraft have crossed the heliopause and entered interstellar space, but they are still vastly closer to the Sun than the expected outer reaches of the Oort Cloud. So how can something be in interstellar space while still being inside the broader gravitational solar system? The answer comes down to the fact that different boundaries are defined by different physical effects. The heliopause is a plasma boundary. It marks the region where the solar wind, the stream of charged particles flowing outward from the Sun, can no longer dominate the surrounding interstellar plasma. Crossing that boundary tells us something about the material surrounding a spacecraft. It does not mean that the gravity of the Sun has suddenly disappeared. Gravity behaves very differently. The gravitational attraction between two objects weakens as they become farther apart. More specifically, gravitational strength follows what is known as an inverse square relationship. If the distance from the Sun doubles, its gravitational pull becomes 4 times weaker. If the distance becomes 3 times greater, the pull becomes 9 times weaker. But there is no particular distance where gravity suddenly drops to nothing. It simply becomes progressively weaker. This means Voyager 1 and Voyager 2 continue to experience the gravitational influence of the Sun even after leaving the heliosphere. The important detail is that neither spacecraft is gravitationally bound to the Sun anymore in the ordinary sense. Their trajectories carry enough energy for them to continue escaping outward, rather than eventually turning around and returning. That gives us 3 related ideas that are easy to mix together. An object can be influenced by the Sun's gravity. An object can be gravitationally bound to the Sun. And an object can travel through a region where the Sun remains the strongest nearby gravitational influence. Those are not necessarily the same thing. Earth is strongly influenced by the Sun and gravitationally bound to it. A distant comet in the Oort Cloud may also remain bound to the Sun, even though the attraction is incredibly weak. Voyager, by contrast, still feels the Sun's gravity, but has enough energy to escape permanently. The farther away we travel, the more complicated the situation becomes, because the Sun is not the only source of gravity. The solar system exists inside the Milky Way. The galaxy contains hundreds of billions of stars, along with gas, dust, dark matter, stellar remnants, and other sources of mass. All of these contribute to a much larger gravitational environment. At ordinary planetary distances, the Sun dominates so strongly that the galactic contribution is almost irrelevant when describing an orbit. But far enough away, that begins to change. Astronomers sometimes describe the Sun's broad gravitational neighbourhood using the idea of a Hill sphere. A Hill sphere is an approximate region around one object where its gravity can dominate the tidal influence of a much larger gravitational system. For the Sun, that larger system is the Milky Way. The idea is useful, but it should not be imagined as a perfectly spherical wall. The true gravitational environment is much messier. The Sun is moving through the galaxy. Nearby stars are moving as well. The distribution of mass in the Milky Way is not perfectly uniform, and extremely distant objects can be disturbed by influences that would barely matter closer to the Sun. Passing stars are particularly important. A star passing within a few light years can exert a small gravitational tug on distant solar system objects. For Earth or Jupiter, that effect would be negligible. For an icy body orbiting tens of thousands of astronomical units from the Sun, the same encounter can matter much more. Its attachment to the Sun is so weak that a passing star may alter the shape of its orbit. It might push the object deeper into the solar system. It might send it farther outward. In some cases, it could even remove the object from the Sun's control completely. Large molecular clouds can produce similar disturbances over longer timescales. These vast regions of gas can contain enormous amounts of mass. If the solar system passes sufficiently close to one during its journey around the Milky Way, the gravitational influence can perturb the most distant objects orbiting the Sun. There is also the galactic tide. This is the subtle difference in the gravitational pull of the Milky Way across the enormous width of the outer solar system. Again, the effect is tiny on human scales, but over millions or billions of years, tiny gravitational influences have plenty of time to accumulate. The result is that the outer gravitational boundary of the solar system is not really a boundary at all. It is a transition. Closer in, motion is overwhelmingly controlled by the Sun. Farther out, the gravitational influence of the wider galaxy becomes increasingly important. Eventually, objects become so weakly attached to the Sun that passing stars, galactic tides, and other disturbances can compete with or overwhelm that attachment. There is no gate to pass through, no alarm sounds, no spacecraft instrument suddenly announces that solar gravity has ended. The neighbourhood simply becomes less clearly dominated by the Sun. The distances involved are enormous. The nearest star system to our own is Alpha Centauri, more than 4 light-years away. That sounds relatively close when compared with the immense size of the Milky Way, but 4 light-years is an extraordinary distance. Even the broadest estimates for the outer solar system leave a great deal of space between the Sun's most distant gravitationally associated objects and neighbouring stars. And these stellar systems are not fixed in place. The Sun moves around the centre of the Milky Way. Alpha Centauri moves along its own galactic path. Other stars pass closer or farther away over immense periods of time. So the geometry of the Sun's gravitational neighbourhood is continually changing. The outer edge today would not necessarily have exactly the same shape or extent hundreds of millions of years from now. This is why the description of Voyager as interstellar is perfectly accurate, while also being incomplete, if we interpret it as meaning that the spacecraft have crossed every meaningful edge of the solar system. They have crossed the heliopause. They have entered the interstellar plasma environment. They are escaping the Sun permanently. But they remain vastly closer to the Sun than the outermost objects that may still be gravitationally bound to it. To find the broadest plausible edge of the solar system, we have to travel much farther. Beyond the planets, beyond the Kuiper Belt, beyond the heliopause, out into a region so distant that its objects can take hundreds of thousands or even millions of years to complete a single orbit. There, almost lost within interstellar space, lies the enormous and still largely hypothetical Oort Cloud. Far beyond the planets, beyond the Kuiper Belt, and even beyond the heliopause, the Sun may still be holding on to an enormous population of icy bodies. This distant region is known as the Oort Cloud. It is not something we have photographed directly. No spacecraft has reached it. No telescope has ever produced an image showing a vast shell of comets surrounding the solar system. Its existence is inferred, and that makes it one of the strangest parts of the solar system, because it may represent the broadest practical edge of the Sun's gravitational family while remaining almost completely invisible. The idea developed from the behaviour of comets. In the early 20th century, Ernst Pick suggested that a distant reservoir of comet-like bodies could exist far beyond the known planets. Then, in 1950, Jan Oort examined the orbits of long-period comets and noticed something important. Many seem to arrive from extremely large distances. Their orbital orientations also suggested that they were not coming from one narrow, flat region. Instead, they appeared from many different directions. Oort argued that the solar system must contain an enormous distant population of icy bodies surrounding the Sun. This became known as the Oort Cloud. Unlike the Kuiper Belt, which is arranged roughly along the broad plane of the planetary system, the Oort Cloud is thought to be much more spherical. Its objects may approach the inner solar system from above, below, or almost any other direction. There may also be more than one broad component. The inner region is sometimes called the inner Oort Cloud, or Hill's Cloud. Farther away lies the outer Oort Cloud, where objects are bound to the Sun only very weakly. Exactly where either region begins or ends remains uncertain. Different models produce different estimates. The inner Oort Cloud may begin somewhere around 1,000 to several thousand astronomical units from the Sun. The outer edge may extend toward roughly 100,000 astronomical units. That distance is almost absurdly large by planetary standards. 100,000 astronomical units is around 1.5 light-years. The nearest star system, Alpha Centauri, lies a little more than 4 light-years away, so the outer reaches of the Oort Cloud may extend a significant fraction of the distance toward neighbouring stars. At that scale, the familiar planetary solar system becomes tiny. Neptune orbits at about 30 astronomical units. Even the heliopause crossed by the Voyager spacecraft lies only a little beyond 100 astronomical units. If the Oort Cloud truly extends toward 100,000 astronomical units, then the part of the solar system containing all 8 major planets occupies only a minute central region. The Oort Cloud probably began forming when the solar system itself was young. During the formation of the giant planets, enormous numbers of smaller icy bodies moved through the outer regions. Jupiter, Saturn, Uranus and Neptune repeatedly disturbed them gravitationally. Some objects were thrown inward. Some were ejected from the solar system entirely. Others were scattered outward onto enormous orbits. If the Sun had formed completely alone, many of those objects might simply have escaped. But the Sun probably formed inside a cluster containing many other young stars. the gravity of nearby stars could have slowed or redirected some of the outward scattered bodies before they escaped completely. Instead of leaving forever, they may have been placed onto vast, weakly bound orbits around the Sun. Over billions of years, those orbits could have evolved into the broad population we now call the Oort Cloud. And the same external forces that may have helped create the cloud can continue disturbing it today. At these distances, the Sun's gravitational hold is extremely weak. A passing star can alter an object's orbit. So can the gravitational tide of the Milky Way. Most of the time, an Oort cloud body may remain far from the Sun, completing an orbit so slowly that one journey can take hundreds of thousands or even millions of years. But occasionally a small gravitational disturbance changes that path. An icy body begins falling inward. As it approaches the Sun, it warms. Frozen gases begin escaping. Dust is released. A coma and tail can form. What had spent most of its existence as a dark frozen object at the edge of the solar system becomes a long-period comet visible from the inner planets. This is one of the main reasons scientists think the Oort cloud exists. Short-period comets, which return relatively frequently, are commonly associated with the Kuiper Belt and scattered disk. Long-period comets can arrive on far more extended orbits and from a much wider range of directions. Their behaviour points toward a distant, more spherical reservoir. But because the Oort cloud itself has never been directly observed, much of its structure remains theoretical. Its estimated population is uncertain. Its inner boundary is uncertain. Its outer boundary is uncertain. Even its shape is likely more complicated than a perfectly smooth sphere. This is not surprising. The farther we move from the Sun, the less strongly the Sun controls everything. The outermost objects may be so weakly bound that encounters with passing stars can strip them away. In other circumstances, the Sun could potentially capture distant material that originated elsewhere. The solar system's edge is therefore not permanent. Its most distant members can be lost, their orbits can change. The surrounding galactic environment can reshape the frontier over enormous spans of time. The Voyager spacecraft give a useful sense of just how extreme these distances are. Voyager 1 and Voyager 2 have been travelling outward for decades and have already crossed the heliopause. Yet at their present speeds, it would take roughly 300 years for them even to approach some estimates of the inner Oort cloud. Passing through the broader Oort cloud could take on the order of 30,000 years. Humanity has reached interstellar space. We are nowhere close to reaching the full gravitational edge of our own solar system, and that finally gives us the clearest answer to the question of where the solar system ends. If we mean the system of major planets, it ends at Neptune. If we mean the main flattened population of distant icy worlds, the Kuiper Belt provides another edge. If we mean the bubble created by the solar wind, the heliopause is the boundary. But if we mean the farthest population of objects still gravitationally associated with the Sun, then the Oort cloud is the best broad answer we currently have. Even then, there is no precise line. The solar system fades gradually into the wider galaxy. The Sun's influence becomes weaker. Passing stars matter more. Galactic tides become more important. And somewhere across that enormous transition, objects that once clearly belonged to the Sun become part of interstellar space instead. The solar system is therefore not simply 8 planets arranged around a star. It is a nested structure of worlds, belts, particles, magnetic fields, and distant frozen bodies. The planets occupy the bright, crowded centre. Around them lies the Kuiper Belt. Farther out, the heliosphere gives way to interstellar plasma, and beyond even that may stretch an almost invisible halo of ancient icy objects, moving so slowly that a single orbit can outlast entire species. At its broadest, the solar system does not finish with a planet, or a wall, or even a visible boundary. It simply becomes less and less the Sun's, until eventually the galaxy takes over. So where does the solar system actually end? The most accurate answer is that there is no single edge. It depends entirely on what we are measuring. Saturn is not an ending, but it is where the solar system begins to feel unmistakably different from the warmer worlds closer to the Sun. Its rings reveal countless particles moving under gravity. Titan carries methane clouds, rain, rivers, lakes and seas beneath an orange atmosphere. Enceladus hides a liquid water ocean beneath its ice and sprays some of that ocean directly into space. The colder solar system is not empty or inactive. It is simply active in different ways. Farther out, Uranus and Neptune form the ice giant frontier. Neptune is the final recognized major planet, orbiting roughly 30 astronomical units from the Sun. But crossing Neptune's orbit does not mean leaving the solar system. Beyond it lies the Kuiper Belt, a vast population of frozen remnants left over from the formation of the planets. Pluto is only one member of that population. And even the Kuiper Belt does not finish neatly. The scattered disk contains objects moving on far more elongated and tilted paths. Detached worlds such as Sedna travel on orbits extending hundreds of astronomical units from the Sun. The farther outward we go, the less the solar system resembles a set of tidy rings. Its structure gradually becomes more diffuse. Then comes another kind of boundary entirely. The heliopause marks the outer edge of the heliosphere, where the solar wind gives way to the surrounding interstellar plasma. Voyager 1 and Voyager 2 have crossed this boundary. In that specific sense, both spacecraft have entered interstellar space. But interstellar space does not mean the Sun has stopped influencing them gravitationally. Gravity has no sharp outer wall. It simply becomes weaker with distance. And this is why the broadest possible edge of the solar system lies much farther away. The Oort Cloud may extend tens of thousands of astronomical units from the Sun, perhaps reaching roughly 100,000 astronomical units in its outermost regions. That would place its distant members around 1.5 light-years away. We have never directly observed the Oort Cloud as a complete structure. Its existence is inferred mainly from long-period comets, gravitational dynamics, and models of how the solar system formed. Its exact boundaries therefore remain uncertain. At those distances, the Sun holds objects only weakly. Passing stars can disturb them. The gravitational field of the Milky Way can slowly reshape their orbits. Some may eventually be pulled away entirely. So even the farthest edge is not permanent. It changes as the Sun moves through the galaxy. The simplest answer is therefore a layered one. The major planets end at Neptune. The main flattened population of icy worlds fades beyond the Kuiper Belt. The Sun's solar wind ends at the heliopause, and the Sun's distant gravitational family probably reaches outward through the Oort Cloud. Almost everything normally shown in diagrams of the solar system occupies only a tiny region near the middle of that much larger structure. Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, and nearly every familiar moon and asteroid are crowded astonishingly close to the Sun when compared with the full possible scale of the system. Earth is not simply one planet among 8 circling a nearby star. It sits deep inside an immense collection of nested environments stretching outward for potentially more than a light year. And if you could somehow drift near the outer reaches of the Oort Cloud and look back toward home, the sun would no longer dominate the sky as it does from Earth. It would appear as a bright star among other stars. Yet even there, faint and distant, its gravity could still be guiding frozen bodies through orbits lasting hundreds of thousands of years. Beyond them, the wider Milky Way would be pulling too, and somewhere in that quiet balance between one star and the galaxy around it, the solar system would finally fade away.